you guys doing today? Now, once again, main focus for me is addressing any questions, concerns you guys have in relation to the test itself, practice test, homeworks and quizzes. So, what's on your minds?
You said the accurate test is easier than the practice test, right?
Yes.
How would you like like,
Well, for one, it's shorter. Practice test is 11 math questions and 12, well, I think like 12 math questions and 5 short answer questions. The actual test is 2 short answer and 7 math. So half the work, maybe, at least 2/3 of the work. And the types of math questions that it has are written by me with the intention of them being something that you can do fairly quickly. Like, for an example, let me think. If I pull up homework chapter 4. So this is homework for question 8. This particular question asks you to solve for several things by analyzing this scenario where there are several forces acting. And this particular question requires several lines of algebra to complete. You have to set up 3 equations with 3 unknowns in them and eventually figure out all 3 of them. So this sort of question is a bit of a time sink, just in terms of how much algebra it takes. I did not write my test questions with the intent of them being time sinks like this, because a homework question you can comfortably do from your room, you can start it and stop it, you can compare notes with your friends. So this being a time sink is kind of part of the exercise. Students work on it together, you can come to tutoring, you can all kind of work with each other to determine the process and then just plug in your own individual numbers. That's why the homework is designed to take time. Tests, though, is meant to be something you're supposed to do by yourself designed for an hour. So each question is written as if it was meant to take you about 7 minutes. So the concepts are similar, like you would need to be able to, for the test, you need to be able to analyze all the forces acting on an individual object, understand that according to Newton's second law, net force equals mass times acceleration, understand that every rope is going to exert the same force on both sides of itself, and how the whole system is going to accelerate together. Those are the concepts I would want you to know from this question, but the test question would be written in such a way that it would not require nearly as many lines of algebra. The setup would be a little bit simpler, or I would give you information to speed up the process. And it likely wouldn't be 3 equations, 3 unknowns. It'd be 2 equations, 2 unknowns at the most. Again, to save you time. Because I write the test as if you're supposed to take it in an hour, but I give you up to 3 anyway. So, one major difference, again, between homework and practice test and the test itself is I have written the test with time in mind. So, in a question like this, if I was to give a version similar to this on the test, it wouldn't be 3 objects. I'd cut it back down to 2. And then try to give you as much information as possible to speed up even the 2 equations, 2 unknowns process. Like maybe guarantee to you that things aren't accelerating, or tell you what the acceleration is so you can better figure things out from there. So the homeworks and the practice tests are kind of a little bit longer to enforce the concepts, but the test questions are shorter and more straightforward since you're supposed to do them in time limit by yourself. Does that answer the question? Okay. So, test has 2/3 the questions of the practice test, and each question I'd say is designed to take half as much or 2/3 as much time. So, I'd say the test, as a rough estimate, would be half as much effort if you understand the concepts on the practice test. That is my approximate goal. All right.
I don't really understand like how you did that. 'Cause I think you said that relative velocity was going to be on the test.
Yeah, you're correct. So 6 is not actually a very good representation of the test itself. I don't know why I included it, if I'm being honest. So I wouldn't stress about this one. If you feel like this one is weird, I'd say this one could be largely ignored. The main thing, if any, that I would point out is, be able to use your various formulas like equation 1 here, and also be able to do unit conversions, because this is working in kilometers per hour, and I ideally would take the answer in seconds. But yeah, I'd just say ignore 6. You can get unit conversion practice in some of the other questions. I apologize.
For number 10, for questions like these, I always I never know if I need to do, if it's supposed to be energy based or use the Fantastic Four equations. So on the test, will it tell me use energy or use?
Yes,
Okay.
if I want you to use energy, I will tell you, but given that the two different methods do work equally well in a lot of scenarios, I usually would lean towards not telling you and seeing what you think to use on your own. Looking at this specific case, here we're dropping an object from a certain height. First question is, what is the ball's speed the moment before impact? You could totally use equation 3 to figure that out, and that would be, not equation 3, equation 4. You could use the old displacement kinematics equations for this question. Frankly, yeah, the only part of this question where you have to use energy is part B, and that's specifically because it mentions, spring constant and elastic potential. So part B is the only part that I'd say you'd have to use energy. You could definitely do A without it. Again, I'd say formula 4, because you want the final speed, you know the distance it falls, and you know the acceleration of gravity. And then, frankly, even the last one, you could jump to an answer without having to do energy calculations. I just wanted to show that in a totally frictionless energy equivalent world, it should rise to the same height, but realistically, things don't bounce up to the same height because you lose energy on impact. But if you didn't, it would bounce up to the same height. So if it asks about springs, odds are it's going to involve energy. But if it's motion and height, you could sidestep the energy part. If it's just motion and falling and height and things like that. Question?
I forget the number, but on chapter 5, the toy gun question.
The chapter 5 homework?
Yeah.
Okay.
Could you cover that?
Yes. Before we move on, did I address your concerns with this one?
Mm-hmm.
Okay. Yeah, if I want energy, I'll say energy. If I don't specify, you could use either method unless it's something specific like the spring part. Chapter 5 homework. Toy gun. All right, this is chapter 4 homework. What am I doing? This one. Now, this one has one trick in it, one small trick. And if I was giving this question on the test, I would only count off 1 or 2 points if you didn't notice it. Unfortunately, web assign is all or nothing. So, but I'm glad you asked. Here we are taking basically a spring cannon, basically the same thing as the one we used in class. It's spring loaded, and firing straight upwards. So the spring is compressed, it's going to push the projectile up, and the projectile is going to gain energy and rise. Before doing any math here, describe for me the energy types that exist at each stage of this interaction. All right, yeah, so between these two pictures, A and B, here we've got EPE. The spring is going to fire, go back to its original length. The ball is going to get pushed upwards, and it is going to gain kinetic energy likely equal to the EPE that the spring loses. So the primary energy transformation here is EPE into KE, since the whole point is compressed spring makes the projectile go. So the main interaction here is EPE into KE, and that would look, I'll keep this one here because that's also chapter 5 homework. Please, I think. So main thing that's happening here is EPE is turning into KE, and again, part A, you don't really have to, you can't grade your answer, so you can input anything here to get points. You should still think about what it's asking about though. Part B says neglecting all resistive forces, so which really just means if friction and air resistance aren't a factor, and we've been treating them like they aren't most of the time. Determine the spring constant of this spring. And I'm going to demonstrate real quick what happens if we use this particular assumption with the numbers given to try to get to the answer. Our initial EPE is going to turn into KE in the marble. The initial EPE is going to be 1/2 times the unknown spring constant times the compression. Everyone's red numbers are randomized, so if you're working along with your own version, keep that in mind. All the red numbers would need to change. Spring is compressed 0.16 meters. Nice that they put it in meters already. Squared, and that is equal to 1/2 times the mass of the marble, 25-gram projectile. In kilograms, that is 0.025. And, hold on. From rest to a maximum, I see. We don't know the speed it fires at. So, quick aside. Yes?
So if you're taking the number before it hits maximum, right? So you can just set the kinetic energy equal to gravitational potential energy once it hits its mass.
Correct. So, you're correct in stating that initially here we've got EPE turning into KE. But then a further stage down the line, as the marble rises up to its maximum height, all that KE is going to turn into GPE. And since we don't actually know the velocity upon exiting the barrel to use here, I'm actually going to go from step 1 to step 3. And we're going to compare EPE to the real final GPE instead. Because we know the height it rises to, but we don't know firing speed. So, instead, we're going to go from stage 1 to stage 3 and directly compare initial EPE to final GPE. That is mass, which is still 0.025 kilograms, times the magnitude of the acceleration of gravity, times the height that it rises to, which is 16 meters. And let's see what the K turns out to be doing it like this. .025 times 9.8 times 16. divided by 0.5 divided by 0.16 squared. And that gives me 306.25 newtons per meter. I'm going to scroll down, and since this is the, oh, look at that. That's actually correct. Now, the teacher version, I see the answers. So right now I'm displaying that that's the answer it's expecting. Questions thus far? Okay. Now, there is a very teeny tiny catch here, and not factoring it in didn't actually hurt us at all working it through this time, but I want to point it out just in the interest of being as accurate as possible. This 16 meters is how far it rises from the spring's end point. Technically, the marble doesn't rise only 16 meters from here, because from this position, the spring is compressed slightly. So the marble's actually beneath the firing point. So technically, a tiny bit of this EVE actually needs to go into getting the marble up to the neutral position and then 16 meters above it. Now factoring that in didn't really hurt us here. We got the answer, but I want to demonstrate, just in the interest of being as accurate as possible, that technically the marble's height increase from here to here is actually the 16 meters in the air plus the 16 centimeters that it rises because the spring springs back up to its original height. And that would actually make the answer bigger, come to think of it. Means it might be less accurate? Weird. Yeah, they made the answer bigger. Weird. Doing the more accurate thing meant I was further away from what Webdesign was expecting. So maybe I'm full of it. Who knows? But it's worth keeping in mind just from a strictly literal analysis standpoint. So in this particular case, you could get the right answer by not factoring that in. It's a very tiny difference. I got 309 doing it the other way. But it is worth noting from a physical reality perspective. Just something that happens if you fire a spring cannon upwards. Also, don't fire a spring cannon upwards because the marble's going to fall back down and you don't want that to be on your head. Anyway, the last question is figuring out firing speed. And once you have spring constant, you could actually do the version I originally mentioned, comparing EPE to the KE that the marble has when leaving the barrel. Now that we have the spring constant, we can solve for that unknown velocity. Make sure that this answer is accurate. Oh, I see. I see. So that's where it comes into play. Also not a big difference that time. So comparing initial EPE to final KE as it is very specifically leaving the barrel gives me 17.7 with my numbers, which is very close to what the design is expecting. Checking one thing real quick. Now, I think that whoever wrote this question was intending for you to factor in that the marble rises by 16 centimeters at this stage. I worked this a second time just on my calculator where I added in technically that there's a tiny little piece of GPE right here since the marble rises 16 centimeters. And doing that only changed my answer from 17.7 to 17.6. So it's a very minor difference, not a big deal. But again, it is worth noting strictly in terms of just describing every possible thing that happens. So if you were working on this one on your own and this final answer isn't quite working, I would take that into account. I would consider that technically there's a little tiny piece of GPE here. Because the marble rises 16 centimeters before leaving the barrel. So some of that initial EPE has to turn into this tiny little piece of GPE, technically speaking. Not a big difference, it's like 0.1, but if WebAssign is being ultra particular about this answer, like you've done this version through and it's not taking this slight modification might help. Does that address your concerns? Yes.
I have a question about, I think it's like number 7 on practice.
All right. This one?
Yeah, so when you're finding force of gravity, why don't you use mass times negative 1.8?
Didn't I? Oh, okay, sorry. That is because in this question, you are told the force of gravity. Notice for each of these two masses, it lists newtons, not kilograms. So these numbers are the forces of gravity. They already solved for that one for you, which means that what I did throughout this process, did I actually show that? Bless you. Yeah, I didn't actually have to solve for mass in this one, weirdly. Yeah, so in this specific question, FG is already worked out for you. Now, if instead it listed mass, you would have to do that, but here that was already done in advance. So do check the units on the pictures, first of all. Newtons is force, kilograms is mass. Is that your main question?
Yes, sir.
Always, always, always check your units. Both the units of your answers, but also the units you are given. Because one, if it's not the base unit, you need to convert it. Like again, if I tell you centimeters, you're gonna wanna make it meters. If I tell you grams, you wanna make it kilograms. But also to make sure you actually know what information you're being given.
I have a question about number 9. Practice test. I don't know why the work is the same as kinetic energy.
So when you throw something, you're doing work, you're exerting force, and you are moving your arm a distance. And what is the goal of the work done while throwing something? Usually the goal is to take what you're throwing and physically give it some velocity in a direction. The goal of throwing is to give the object you are throwing a velocity, to make it move. Now, part A, you're given the force of the throw, you're given the distance. You can figure out the work done by this pitch. And this means that, using these numbers, your arm uses up 160 joules worth of energy. That energy is now no longer in your arm. So where does it go? To the ball. Hold, please. I'm about to sneeze. Apparently, if I acknowledge the sneeze, it goes away. Maybe it's shy. Anyway. Yes, when you throw something, you do work. You send energy out of your arm. That energy has to go somewhere because of law of conservation of energy. And since the goal of throwing is to make the ball move, the ball is going to gain that energy in the kinetic form. So assuming ideal conditions and no energy loss, all the work you do would become kinetic energy in the ball. And if it has that much kinetic energy, you can figure out what its speed would be at that energy level. This is an ideal, so like mitigating all friction and outside factors, this person could hypothetically clock 46 meters per second on throw, which is very fast.
So is work always going to be like equal to kinetic energy for throwing something?
For throwing something, yes. Now, exactly what role the work performs is going to kind of depend on the scenario. I can actually show you an example of basically the reverse of this, because when you're throwing something, the work you do is to give something kinetic energy, but my previous section asked about a homework problem where the opposite happens. Nope, that's chapter 4. Is this chapter 5? Yes. This is homework question, homework 5, question 8. Where is it? No, it's 3. Homework 5, question 3. And this is the reverse scenario. When you are throwing, you are doing work to give some kinetic energy. But what's happening here is a projectile is going to strike a stationary object and bury itself a certain distance into it. So actually, I've got the work for it over here. And here the reverse happens. Initially, the projectile has kinetic energy, and what's going to happen is, as it strikes the tree trunk is going to exert force on it. The projectile forces on the trunk, and therefore the trunk is going to force back. As the projectile buries itself a certain distance into it. So that's a force and a displacement, meaning that here the trunk is actually doing negative work to take energy away from the projectile. So here it's technically the same relationship, just reversed. But there's other scenarios, like say lifting something straight upwards, where the work I'm doing instead turns into GPE. The main thing with work is you are always giving energy to something, and that energy has to be in some form, or you are taking energy away from it. So if there's ever work, either something has to gain energy and you have to figure out what form it's going to be in, or it's taking energy that already exists in some form away from it. So whenever there's work, it's worth looking at the situation and thinking about what form of energy is something gaining, or what form of energy is being taken away. Bless you. And exactly how that works is going to depend on the question. Related example, when I do this, that's force and distance on behalf of my hand, and here the energy being gained is EPE. So again, it's going to depend on the exact scenario. I'd say the main rule, and I'm repeating myself, sorry. The rule that I would say to keep in mind is positive work always gives something energy in some form, and negative work always takes energy away in some form. Does that address your question? Mm-hmm. Okay. How do you guys feel? What else is on your minds?
Okay, I have one more question.
Okay.
So, for 3 on the practice test, I know how to do it, but when I was doing like the quadratic for it, like your positive time was my negative time.
Oh.
And I don't know how I did that.
Well, let's take a look. Okay. I think the signs would be swapped if the 17.7 on the front wasn't negative. Because the Pythagorean theorem dictates that it's negative b plus minus. And the b value should originally be positive and therefore become negative. That would switch them.
That one, I left that one negative, but okay, for 4.9 in the equation above, I have mine positive.
Okay. Yeah, that. You got the same numbers, just inverted?
Yes.
Interesting. Yeah, that would be part of it, because if this was inverted, then this bottom would be positive instead of negative, and that would also switch the signs. Weirdly, that would affect what's going on inside of the square root as well. I'm wondering, what sign did you give the 30 in here?
The 30 was negative.
Okay. Now, initially, yes, the 30 is negative, but to get everything onto the correct side of the equation and into A, B, C form, the way I wrote it, it actually wound up being positive before I put it in. So, if, yes, the signs on these two things were switched, if you had positive 4.9 and negative 30 once you got them all on the right side and made them A, B, and C, that would totally flip the signs of your answers.
Okay. So, delta y is negative?
Originally, yeah, well, the way I originally wrote it here, yes. Normal delta y, final position minus initial position, or final height minus initial height, is negative the way that I set this up. Specifically because the wall's final height is down here, and its initial height is up here. It ends beneath where it began. Now, that would be reversed if the object stopped above where it began. Like say you were on the ground trying to throw up to a cliff edge. So, always keep in mind, delta anything is final minus initial. If you end below where you begin, it's negative. If you end above where you begin, it's positive. Now, let's actually look at the times themselves real quick. When I look at these, they make sense to me because these, again, your formula doesn't really understand the physical situation. It just knows Pythagorean theorem. These are the two numbers it spits out. And what these numbers would physically represent is launching from this cliff, the ball would land on the ground 4.9 seconds after the firing happens. The negative number would represent the points in time it would happen in the past if instead of from launching here, it launched from some hypothetical position inside the cliff in the past, which again makes no physical sense. It's just giving you the point on the parabola where that time would mathematically work. And if these were switched, that would imply that, like if this was the positive number, it would imply that the ball would hit the ground really fast, and that somehow that hypothetical backwards time would be 5 seconds into the past, which, given that this is a much shorter distance than this, doesn't make that much sense. Again, it's just kind of tracking through the invisible parabola here. Does that address your concerns with this one? Okay. Yeah, the Pythagorean theorem spitting out a negative is, it's always weird to think about what it means, but it's worth considering if your signs do get switched by accident, does which one being negative make sense? And sometimes it's not only the negative sign, but also the size of the number. It makes sense that it takes more time to go up and down than it would go to just go straight down into the cliff in backwards time. Now sometimes the Pythagorean theorem can give you two positives. So I actually want to talk about that fringe case now that I'm thinking about it. It can give you two positives, and the main case where I can think of where that would happen in terms of projectile motion the main case that I know of is if you do something like this. Similar scenario, it's still projectile motion, it's still, two-axis initial velocity, figure out time in the air, figure out how far it goes. It's just you're ending above where you begin. And that would switch this sign, meaning it would be negative here, negative there, and ultimately that has the potential, actually that would give you two positive numbers here. And again, just to kind of explain what that means, those two positive numbers represent the two times where the marble is at this height. But the smaller of those two times, you're just passing it on your way up. And the second of those two times, you're coming back down to actually hit the cliff. So, every time you do the quadratic, it is worth looking at the numbers themselves to determine, does what you got make sense? Not just in terms of positive and negative, but in terms of the size of the two numbers and then considering which of the two you want to use.
So the bigger number is usually like the correct one.
Yes, for our projectile motion questions, yes.
If there's tension in like two ropes and they have the same angle, do we just assume that they're like the same tension?
Oh, yeah, you mean the flower pot?
Yeah.
Yeah, here they worked out to be the same because they are mirrors of one another. And here they'd have to be the same tension in order for their X components to cancel out, and then their Y components each take half of the load. I want to actually highlight a similar homework question that I've been asked about, which is chapter 4, number teeth, number 6.
Yeah.
This is technically the same thing. It's two forces, two tensions, pulling away at the same angle from a fixed point. The weird part about this one is just the entire perspective is tilted, but you could redraw it traditionally, and it would give you the same basic process. The X components cancel out, and the two Y forces add up together in the same direction. But that only happens if the angles are the same. If they are different, they would likely have, even if their X components do cancel out, their Y components wouldn't match and the overall tensions wouldn't match. There's a surprising amount of math that goes into orthodontics. How you guys feel?
So for number 4, on the practice test, the normal force isn't equal to the force of gravity because the rope of the sled is also pulling a little bit up.
Yes, and I apologize that my answer key doesn't actually show how I got that number. I just made a mistake when I was making it and didn't write that part down. But conveniently, someone else asked, so I have it written under the board. Yes, here the normal force is not equal to gravity because there are 3 y-axis forces here that must add up to 0. Normal force up, gravity down, and the y component of the rope's tension up. And if normal force and gravity are the only 2 vertical forces, usually they'll, be equal and opposite. But this scenario is kind of like, well, when I was first teaching about normal force, I mentioned that if you were standing on a bathroom scale, you can lift yourself up using the edge of the counter, and that reduces the number on the scale, even though that doesn't literally change how much you weigh, because the scale doesn't know how much you weigh. The scale just tells you the normal force it is exerting to hold you up. Same thing here. Since the rope is tilted upwards, given that most people tend to be taller than the things that they're dragging, since the rope is angled up and there's a vertical force, that is kind of reducing the burden of the earth beneath it. Normal force doesn't have to be as big. If that vertical component just wasn't there, normal force and gravity would have to cancel out to 0. But since it is there, that reduces the burden of the normal force, decreasing it to 174.3. So, never automatically assume normal force and gravity are equal and opposite. They can be opposite and unequal, and they can also be unequal and unopposite in the case of on a ramp. Because here they are neither the same number nor in the opposite direction as each other. They are not automatically equal or opposite. There's just a specific scenario where they are, which is to say, sitting on flat ground, not accelerating up or down, and there is no other forces in the vertical axis. Often equal and opposite, but not by definition equal and opposite. Does that help with this one? I apologize again for that missing from my answer key. I assume I was working on this one, and then my phone went off. And then when I turned back to my work, I thought, all right, this one looks done, moving on. Oh, the net force? So the trick to assuming that the net force on the sled is 0 is noting up there constant velocity. Constant velocity means acceleration of 0. If acceleration is 0, net force is 0. And that's why when I wrote down the net force in each axis, I knew that everything had to add up to 0 in both axes. That's the only way to be moving at constant speed. This tells us, again, that these 3 things add up to 0, and likewise, if the x net force is 0, that means that there has to be some amount of friction negating the rope's x component forward. If friction wasn't here, then frankly this wouldn't be equal to 0 if you were pulling, and so you'd just be accelerating forwards in that case. So constant speed, everything cancels out, and that means force forward is usually negating the friction backwards, and that's how cruise control works. It just sets your car's force forwards to be enough to negate friction and keep you at the same speed. And that's usually why the cruise control is never super accurate, at least in my experience. When I turn cruise on, it often wiggles around 5 miles per hour, whatever I set it at, because the computer has to constantly be calculating force requirement, and that's constantly changing whenever you're, if the road gets bumpier or if you're going up or down a hill. Sometimes it even changes gear while trying to maintain the same speed, and you hear it suddenly rev, even though the speed doesn't change all that much. At least that happens in my automatic. You're doing them. I don't know if manuals have cruise control.
So for part C of that, when you define the magnitude of the rope's force, you have to show that different values for x and y. It's not just 100 newtons.
Well, all I asked for was the magnitude of these forces, and so technically if that was all I asked, that is the answer, that is the strength of the force. I only wrote this here for the benefit of students reading it, knowing that is the magnitude, but since it's got components, those components are what make it into the axes calculations. But if magnitude is all I ask you for, then the one original number will suffice. So that was me giving more information than I would have wanted, just because I over-explain things.
And you said to ignore 6 or
Yes, I would ignore 6. That one's relative velocity, and there's not relative velocity in the test. I never really talked about it in class. And what was my next point? The other parts of 6 that I would consider useful practice are like better gotten elsewhere, just like unit conversions and using formulas. So my official instructions are you can ignore practice test question 6. Yes.
Can you do or explain chapter 3 homework number 3?
Chapter 3, number 3. This one?
Mm-hmm.
All right, so here we've got 2 people pulling on a mule, which is generally not recommended. Those things will kick and will bite. Each person is exerting a different force at a different angle. And the first question is basically asking what is the lump sum, the net force of the 2 humans added together? So we got both of them exerting different forces in different directions. Part A wants to know what are those 2 forces added together? So it might be saying it in kind of a weird way. Find the single force that is equivalent to the 2 forces shown. It's kind of getting to the implication of if you had a third person that could pull with this strength in this direction, that would be equivalent to what these 2 are doing. So, what could you replace the pair of them with? But basically it just wants to know the net force. What is the effective overall combination? Why can't I talk? I'm gonna decide on how to say this one. What are those 2 forces added together, magnitude and direction? Would you like to do that one?
Sure.
Okay. So, this is vector addition, and since both of those forces are on angles, one would need to break them both down into their components before you did any work to them. So, again, everyone's red numbers will be different. I've got 74 newtons this way at 75 degrees. That's technically F2, so we'll do F2y, F2x, 74 newtons. And separately, that's going to get added to 149 newtons. So one of these 2 guys skipped arm day. Oh, 60 newtons, that's still more up than over. 60 degrees. So these are the 2 vectors we need to add together. So we're going to eventually add the x's and the y's. We just need to figure out the components first. So, this one's F1, so I'll do it first. From this 60 degrees perspective, we work our way through SOHCAHTOA. Sine is opposite of hypotenuse. Which leg is opposite the 60 degrees? F1y. So sine of 60 is going to be F1y over 148. Meanwhile, cosine of 60 will be F1x over 148. And we can determine numbers for the two of them. Same basic operation for vector 2. Main difference is just the two numbers that we're plugging in. But the angle is just basically mirror oriented, so sine should still tell us y and cosine should still tell us x, but never take that for granted, because if hypothetically it gave us this angle instead, that would switch. So do check before you just assume. Sine of 75 would be f2y over 74. Cosine of 75 will be f2x over 74. And that's going to give us 4 different numbers that we have to do something with. And we'll check what those numbers are. Sine of 60 times 148. F1y should be 128.2 pointed up. F1x is 74, coincidence of coincidences. Pointed positive x to the right. Just based on the picture, this leg would point that way. Meanwhile, for F2, we've got sine of 75 times 74, which would be 71.5 newtons, also pointed up. And the x component would be 19.2 newtons, pointed to the left, based on the picture. I've been writing down those arrows to try to make it clear which of the two legs work together versus which of the two work against each other. The two y legs both point up, and so they have good teamwork in the forward upward direction, but they are working against each other in the x-axis. So when it comes time to actually add these vectors together, I'd just like to show that vertically. The two x legs need to have opposite signs. Oops, I wrote that backwards. Negative 19.2 and positive 71.5. The x legs have opposite signs because they point in opposite directions, whereas the y legs both point in the same direction. They have the same sign. And so the x component of the final sum force is 54.8, and the y component of the final sum force is 199.7 approximately. So those are the components of the final answer. All of my markers are dying. Are those numbers legible, factoring in that I'm running out of ink? Oh geez, we ran out of time 3 minutes ago. Whoops.
Sorry.
It's okay. To get to these final numbers, again, you should treat these as the legs of a new triangle. You have to solve for magnitude and hypotenuse. That would be the answer here. The answer to the second part would be the same, because it's asking what third force would cancel these two out. It would point same magnitude as this, but opposite direction, 180 degrees away. Try to very quickly demonstrate. This force would look something like this. And our part B is asking about a force directly opposite it that would negate that vector sum.
Yeah.
So whatever angle you get here, add 180. And that would be the answer to part B.
Okay. I think I made it a little bit more complicated just because the wording was weird,
That's fair.
but I was definitely on the right track. But it was like the adding the 180 and just finishing it.
Yeah, and that's why on the test, if you are ever confused when you are being asked, please ask me. I want to make sure that that is not an issue.
Thank you.
Welcome.
Sorry, we went over for it.
Sometimes I get on a roll and I forget what time exists.